Good morning. So in the last class, we have discussed about the controllability test by using the Kalman's test as well as Gilbert test. And today we discuss about the observability. So how do you say the system is observable? How do you say the system is observable? So that is in the last class controllability we have done with the two tests, that is Kalman's as well as Gilbert. Today the same way observability can be done by two tests, that is Kalman's as well as Gilbert. So before going to that, what is observability? What is observability? We need to find out. So it is nothing but it is the determining of it is determining of the system state by measuring the output by measuring the output for finite length of time. Finite length of time. So here determining the system state by measuring the output of the system for the finite length of the times. So then if you define clearly, when I want to say the system is completely observable, so observability is nothing but we need to find out the system state. We need to find out the system state by measuring the output of the system for a finite length of the time. So if I want to say the system which is completely observable. So a system is said to be completely observable. That is, if it is, identified, every state is identified by measurements of output, by measurements of the outputs, measurement of the outputs. So every state is identified by the measurements of the outputs, by the measurements of the output or finite time interval. So here how we are going to say that the system is completely observable? If every state is identified by the measurements of the outputs over a finite interval of time. So if the system is not completely observable, means we cannot measure the output. So when you say the completely not observable, when you say completely not observable, means, so if you are not able to identify, or if you are not practically not able to measure, the outputs, practically not able to measure the outputs, not able to measure the outputs, then we can say the system is completely not observable, because we are not able to measure the output. We cannot able to measure the output which are shielded from the observation. So the output are shielded from the observation. So those systems are called as completely not observable, where we can measure the output of the system over a finite interval time. Then we can say the system is completely observable, and we can identify the every state. We can identify the every state, or we can determine the state of the system. We can determine the state of the system by measuring the output of the system for a finite or a finite length of the time. So this is what is meant by observability. So what is the definition of observability? When we say the system is completely observable, and when we say completely not observable. So based on that, similar to that, what controllability, how we have tested, the observability of the system can be obtained by using two tests. What are those two tests? Are Kalman's test and as well as Gilbert test. So this observability is tested by Kalman's, similar to the controllability, and as well as Gilbert test. So in the case of controllability, we have measured the by using the Kalman state by writing the composite matrix, where the composite matrix we have written. So controllability of the by Kalman's test. Yesterday's class we discussed about the Kalman's test, where we are going to write the composite matrix, which consists of the columns B, then AB and A square B, and so on, a to the power of n minus 1 into B. So here, similarly, the observability test, similar to that, we did to write the composite matrix, but the elements of this matrix are different than the controllability. So the controllability B matrix AB and A square B, a to the power of n minus 1 B. But in the QC, if you look at, the elements are C transpose, means which are, because the observability depends on measurement of the output. So output equation, we know that y is equal to cx, plus du. So the maximum the input variable may not be present in the output equation. So that's why the C transpose matrix is taken, and then A transpose C transpose, because it depends on the output variable. So, and C transpose, A transpose, C transpose, and so on. We can take it as A transpose whole square into C transpose, and so on. A transpose whole to the power of n minus 1 into C transpose. So this is the matrix which you need to write, that is the composite matrix, compared to this controllability and observability. See, the controllability is with B, AB and A square, because this is a state equation, whereas because we are finding the transferring the initial state to the desired state in the controllability test, whereas in the observability test, based on the measurement of the output, we are going to find out the state of the system. Identify the state of the system. So that's why measurement of output we need to do here. So that's why in the output equation, so output equation is considered in the observability test. That is y is equal to cx plus du, and C transpose matrix is taken to calculation, because C represents the output equation. So with the state variable, with the relation with the state variable, so C transpose, then A transpose, C transpose, and so on. So transpose in the sense matrix C is to be transposed. Now this is about the Kalman's test. Whereas in the controllability, we have conducted the Gilbert test also to test the controllable, whether the system is completely controllable or not. Gilbert test. So what is the Gilbert test? We have written the vector matrix B, which is written as like this. Vector B matrix is equal to M inverse B. So where M is the model matrix. So we need to find out the model matrix also. We have know that the model matrix is written as with the eigenvalues, that is lambda 1, lambda 2 and lambda 3, lambda 1 square, lambda 2 square and lambda 3 square. That's what we have done in the previous class. So Gilbert test of controllability we can find out by using this M inverse B, vector B matrix is equal to M inverse into B. Similarly, here in the Gilbert test, we are going to find out the one more vector matrix, that is the output matrix. Vector C matrix, which is represented as C cap. There I am going to represent this in with C into M. So find out the vector matrix C cap is equal to C into M, where we can say C into M in the sense M is the model matrix. So you can find out the model matrix CM, which is similar to this. M is equal to with the eigenvalues, I am going to write 1, 1, 1, lambda 1, lambda 2, lambda 3, lambda 1 square, lambda 2 square, lambda 3 square, and so on. So here, similar to that, we are going to find out the this CM matrix. Once you find out the CM matrix, then the system, which is if all the coefficient, I mean, if all the elements of this vector C matrix are non-zero, then we can say it is completely observable. Completely observable. Okay, so here we need to understand this Kalman test and Gilbert test for the observability by doing one example. So we'll take one example here. Yeah. So here, evaluate the observability of the system. Evaluate the observability. Of the system. Okay, which is given as the matrix are given. So the matrix are given, which we can take it as A is equal to 0, 1, 0, then 0, 0, 1, then 0, minus 2, minus 3. Then B is equal to 0, 0, 1, then and 4. So these are the matrix of the state equation. These are the matrix which are presented in the state equation. This is the matrix which is present in the output equation. Y is equal to Cx. Here this is x dot is equal to Ax plus B into U. Okay. So if you look at here, the order of the matrix which is given as 3 by 3, that is n is equal to 3 now. N is the 3. So you write the observability matrix. So observability matrix or composite matrix, you can take it as, okay, we can take the differentiation for the QC of the controllability and observability. We will take here Q naught. So okay. So in the previous we have taken for composite matrix here to so this is C and this is O. So I'll take this observability. Okay. So Q naught we will be taking for the observability test, so that it will be easy for identifying the Q naught and QCs. QC is for controllability test. Composite matrix we are going to do for the controllability test, and Q naught is going to be, we are going to write for the observability composite matrix for observability test. So Q naught is equal to, we have the equation that is C transpose, where n is equal to 3. So then second column is, so A transpose into C transpose, and A transpose C whole to the power of n minus 1. We need to, up to this we need to go. So n minus 1 is equal to 3 minus 1, which is up to square we need to do. So A transpose whole square into C transpose. So this is what we need to do observability test by using the Kalman's, test. So this is about Kalman's test. We are going to find out the observability matrix, which is written as C transpose into, C transpose. Second column is A transpose, C transpose. Third column is A transpose whole square, C transpose. Why I have stopped at A transpose whole square means, because up to A transpose whole to the power of n minus 1. So where n is equal to 3, order of the matrix. So 3 minus 1 is 2. So up to the A transpose whole square, we need to do these columns to be added up to this A transpose whole square. Now each one we need to calculate here. So C, we know that C matrix is equal to 3, 4, 1. So which is 1 by 3. So C transpose will become 3 by 1. C transpose means rows are converted into a columns. That is 3, 4, 1. So C transpose is nothing but 3 by 1 matrix. So once you write the state transpose, then we need to write the A transpose also. So what we have the A? What we have the A is 0, 0, 1. Sorry, 0, 1, 0. So A we have 0, 1, 0. 0, 0, 1, 0, minus 2. So here I am writing this first row as first column. So if I write the A transpose, is equal to, So 0, 1, 0. So I have written this row as a column. Then second row as a second column, that is 0, 0, 1. And third row as a third column, 0, minus 2, minus 3. So I have written this. So this is A transpose. This is A transpose. Now we need to calculate the A transpose into C transpose. If I want to find this each column matrix, so C transpose is obtained, then A transpose into C transpose we need to find out. So A transpose into C transpose, which is equal to 0, 0, 0, 1, 0, minus 2, then 0, 1, minus 3. So where C transpose is nothing but 3, 4, 1. So it is 3 by 3 and this is 3 by 1. So resultant will be 3 by 1. Resultant will be 3 by 1 matrix. So now calculate this 0 into this, 0 into this, that is I am writing 0 into 3 plus 0 into 4 plus 0 into 1. So 0 into 3, 0 into 4, 0 into 1, that is the first column, first element in the matrix A transpose into C transpose. So now similarly second row 1 into 3. So we need to write the 1 into 3 plus 0 into 4 plus minus 2 into 1. Then third one, that is 0 into 3, 0 into 3 plus 1 into 4 plus minus 3 into 1. So then, so after simplification, what I'm going to get? So I'm going to get 0, this will become 0, this will become 0, this will become 0. So first one is 0. Then this is 3, this is 0, and minus 2 into 1. So 3 minus 2, 3 minus 2 will become, you're going to get 1. This is 0, 1 into 4 plus minus 3. 4 minus 3, it is going to be 1. So I got A transpose, C transpose is equal to 0, 1, 1. So now what I have to do is, I have to multiply this A transpose whole square. So I can write this as A transpose whole square into C transpose. So here I can use a simple way of calculation, that is A transpose into C transpose. So I can use already A transpose into C transpose, the resultant is there. So I can use the A transpose is 0, 0, 0, 1, 0, minus 2, then 0, 1, minus 3. Then already the resultant of these two is obtained. So where, which is equal to this much, that is 0, 1, 1. So I just write the 0, 1, 1 is the resultant of A transpose, C transpose. So this matrix talks about the A transpose, and this matrix is about the A transpose into C transpose, A transpose into C transpose. So put together A transpose whole square into C transpose I'm going to get. So here this is a 3 by 1 matrix, 3 by 3 matrix, and this is 3 by 1 matrix. So resultant will be 3 by 1. Resultant will be 3 by 1. So find out this resultant, which is so 0 into 0 plus 0 into 1 plus 0 into 1. Then second row 1 into 0 plus 0 into 1 plus minus 2 into 1. Then 0 into 0 plus 1 into 1 plus minus 3 into 1. So the resultant, if I write the equation here, if I write the matrix 0, this will become 0, this will become 0, and this is also 0. So element is 0. 1 into 0, 0. Then this is also 0 into 1, 0. So these two will be eliminated. Then minus 2 into 1. So I will be getting minus 2. Then 0 into 0, 0. 1 into 1, 1. Plus minus 3 into 1. So minus 1 minus 3, I will be getting minus 2. So 0, minus 2 is the elements of A transpose whole square into C transpose. Now I'll write the Q naught matrix or Q observable matrix. So Q naught is equal to, we know that C transpose, then second column is A transpose, C transpose, third column is A transpose whole square into C transpose. Okay, so now each column is going to be filled here. So what is the C transpose matrix? So from here we can get to know that C transpose matrix is 3, 4, 1. So 3, 4, 1 is the C transpose matrix. 3, 4, 1. Then A transpose into C transpose matrix from the above. See, this is the A transpose and C transpose matrix, the resultant one. So I'll take that. I'll take that now. That is 0, 1, 1. Next is we need to find out this A transpose, C transpose matrix. So this is the resultant of A transpose whole square into C transpose matrix. So I'll write down that 0, minus 2, minus 2. So now I have written this Q naught matrix. I have written the Q naught matrix. So once you written the Q naught matrix, we need to find out the rank of this Q naught matrix. Rank of this Q naught matrix. So we can find here. So before finding the rank of the matrix, determinant of the Q naught is going to be find out. So that is 3, 4, 1, 0, 1, 1, determinant of this matrix. So determinant of this matrix, it will take 3 into minus 1 into minus 2, okay, minus once again 1 into minus 2, so plus minus 0 into anything is going to be 0, then plus 0 into anything is going to be 0. So if I find out this 1 into 3 into 1 into minus 2 is minus 2, then minus of minus 2 is going to be plus 2. So 3 into 0, so this is going to be 0. It is determinant of Q naught is equal to 0. So it means that the rank of matrix, here we can take it as less than the 3, because it will not be 3 if it is not equal to 0. If it is a non-zero value, then the rank of matrix is going to be is equal to 3. But here the rank of the matrix, where we are going to get this determinant is equal to 0, so the rank of the matrix is not equal to 3. So it is less than the 3 value. It will be less than the 3 value. So here, that is why what we can write is the rank of the Q naught matrix. The rank of the Q naught matrix is not equal to the order of the matrix. So rank of Q naught is not equal to the 3. Why? Because it is not equal to the order of the matrix, not equal to the order of the matrix. So when it is not equal to the order of the matrix, we can say the system is not completely observable. Not completely observable. So hence the system we can say, is not completely observable. Not completely observable. So output is shielded. Output is shielded. So here we need to find out the rank of the matrix of Q naught. So where Q naught is determined is non-zero value, then we can say rank of the matrix is going to be 3. As it is not equal to 0, as it is not containing the non-zero value, it is equal to 0. So the rank of the matrix will be less than the 3 value. Less than the 3 value. So here the rank of the Q naught, which is we are expecting that it should be a 3, but it is not equal to 3. It is not equal to 3. So rank of the matrix is not equal to 3. So 3, why you are taking is because the order of the matrix. It is not equal to the order of the matrix, that is n. So hence the system is not completely observable. If Q naught is equal to 3, then with the system is completely observable. When it is going to be Q naught is equal to 3, when the rank of the when the determinant of the Q naught matrix is non-zero value. So here determinant of the matrix is 0 value, then the rank of the matrix always less than 3 only, as well as less than 3. So it never be equal to 3. So that is why rank of the matrix is not equal to 3. Hence the system is not completely observable. Right. So this is about the what you call the Kalman test of the observability, Kalman test of the observability. So how to find out the similar way the for the same kind of system by using Gilbert test, by using Gilbert test, Gilbert test. So as we told that we need to find out the vector C matrix which is equal to C into M. So what is the C value is the the C matrix is obtained from the output equation, and the M is the model matrix. M is the model matrix. So we have given in the problem A is 0 1 0, then 0 0 1, then we have given 0 minus 2 minus 3, then we have the B matrix as 0 0 1, then C matrix as 3 4 1. So if you look at here, I need to find out the model matrix. If I want to find out the model matrix, which is contains of the eigenvalues, which contains of eigenvalues, that is lambda 1, lambda 2, lambda 3, lambda 1 square, lambda 2 square, lambda 3 square. The elements are eigenvalues. So in order to find out the eigenvalues, we have the equation, that is characteristic equation lambda I minus A equal to 0. So determinant of lambda I minus I equal to 0. So by using this characteristic equation, I'll find out the eigenvalues. So here substitute that determinant of lambda into I. I is depends on the order of the matrix A. So order of the matrix is 3 by 3. So this identity matrix also should be 3 by 3. 1 0 0 0 0 1. Sorry, 0 1 0 0 1 0. 0 0 1. So this is the identity matrix. Then minus A. So A we have that 0 1 0 0 0 1. Then 0 minus 2 minus 3. So lambda is multiplied to this. We are going to get lambda 0 0 0 lambda 0 0 0 lambda, determinant of this, then 0 1 0 0 0 1 0 minus 2 minus 3. Then we need to subtract this matrix from the first matrix to the second matrix. So subtraction is done now. So here mod of lambda minus 0, that is corresponding elements means, so first element of this, second, first row, second element, those are called as corresponding values. So we need to find out the lambda minus 0 lambda. So then it is going to be, second one is going to be 0 minus 1, then third one is 0 minus 0, so lambda minus 0, then 0 minus 0, lambda minus 0, then 0 minus 1, then 0 minus 0, then we have the 0 minus of minus 2, then lambda minus of minus 3 equal to 0. Now if I simplify this, we can get lambda minus 1 0, this is 0, and lambda minus 1, then 0, then it is going to be 2, and it is going to be lambda plus 3. So determinant of this we need to find. So by determinant, how we are going to find out is this into this. So lambda into lambda plus 3 minus of 2 into minus 1. This is for this one, and for this one, that is minus of -1 means I need to take this and this. So cancel out this and this. Okay. So then minus of -1 into minus of -1 into 0 into this, 0 into lambda plus 3 minus 0 into -1. So equal to 0. So this is, if I take into lambda square plus 3 lambda minus of minus plus 2, then minus of minus plus 1, this whole thing will become 0 minus 0. So this 0 minus 0, I'm going to get 0. 1 into 0 is equal to 0. So I'll be getting lambda cube plus 3 lambda square plus 2 lambda equal to 0. So from this we can get the equation as, so you can take out the lambda. So lambda into lambda square plus 3 lambda plus 2 equal to 0. So that is lambda equal to 0. And the equate this lambda square plus 3 lambda into, so I'll be getting around this factorizing. So factorizing, some multiplication should be 2 and then sum is going to be 3. So I can write as lambda into lambda square plus lambda plus 2 lambda plus 2 equal to 0. Then lambda is equal to lambda into lambda plus 1 plus 2, you can take it as lambda plus 1 equal to 0. Then we find out as lambda into lambda plus 1 into lambda plus 2 equal to 0. So we can take it as lambda 1 is equal to 0, lambda 2 is equal to -1, lambda 3 is equal to -2. So we have got the eigenvalues. Once we got the eigenvalues, we need to find out the model matrix. So model matrix is equal to 1 1 1 lambda 1 lambda 2 lambda 3 lambda 1 square lambda 2 square lambda 3 square. Okay, so now I substitute the values 1 1 1, lambda 1 is 0, lambda 2 is -1, lambda 3 is -2, lambda 1 square is 0, lambda 2 square is 1, and this is going to be 4. So once you got the model matrix, then I need to find out the vector C matrix. Vector C matrix, that is vector C matrix is equal to C into N. C into N. So we know that the C matrix is given as 3 4 1, then M is given as 1 1 1 0 -1 -2 0 1 and 4. So by using this 2 matrix, substitute in the above vector C matrix. So then I can find out C is equal to 3 4 1, and then M is 1 1 1 0 -1 -2 and 0 1 4. So what is the outer of this matrix? So this is going to be 1 by 3 and this is going to be 3 by 3. So resultant will be 1 by 3. Resultant will be 1 by 3. So now I'll write the resultant matrix. So this row and this column. This row and this column. So first we'll write down the 3 into 1 plus 4 into 0 plus 1 into 0 plus 1 into 0. This is the first element in the C matrix. Then second element, same row, second column. So same row is same, second column, that is 3 into 1 plus 4 into -1 plus 1 into 1. Then same row and third column. Third column element we need to find out, that is 3 into 1 plus 4 into minus 2 plus 1 into 4. So this is the matrix which I have got the resultant of 1 by 3. C matrix is resultant of 1 by 3. Now, by simplification, this is going to be 3 plus 4 into 0, 0, 1 into 0, 0. So I'm going to get 3. And similarly, here 3 into 1 is 3, minus 4 plus 1. Then 3 minus 8 plus 4. So I'll be getting 3 plus 1. 4 minus 4, 0. And 7 minus 8, minus 1. So if you look at this matrix, if you look at this matrix, I'm getting here is the 0 element. So C matrix contains, vector C matrix contains 0 element. It means that the system is not completely observable. So as there is 0 in the matrix, in matrix C, the system is not completely observable. Not completely observable. So this is how we can say the system observability by using Gilbert test. So here in the state variable system, we have to test the controllability and observability. So controllability is nothing but whether system can be able to transfer from the initial state to the desired state or not. Initial state to the desired state or not. So that we can do, that we can check by using Kalman's test and Gilbert test. And similarly, observability, where we can able to determine the state of the system, by measuring output. So how to check whether the system can be able to determine the state of the system? So once again, we can check with the Kalman's test and as well as Gilbert test. Okay, so this Kalman test and Gilbert test for both the controllability and observability, how we are going to conduct this. Okay, so that we write in one step. So Kalman's test, here we write QC, which is equal to the matrix B, AB, then A square B, and so on, A to the power of n minus 1 into B. Whereas here Kalman's test, we write the Q0 matrix, where we are going to write the a matrix of transpose matrix, C transpose, okay, and then A transpose, C transpose, then A transpose whole square, C transpose, and so on, A transpose whole to the power of n minus 1 into C transpose out. So this is about the Kalman's test for the observability, and Gilbert test for controllability is, we are going to find out the B matrix as n inverse into B, and here we are going to find out this vector C matrix, which is C into M. So when we are going to say this QC, rank of the QC is equal to the order of the matrix, rank of the QC is equal to order of the matrix, then we can say the system is completely controllable. Similarly, here also the rank of the Q0 matrix is order of the matrix, then we can say the system is completely observable. Similarly, Gilbert test, if I check out the controllability, you need to check out the vector B matrix elements. If it contains non-zero elements, we can say the system is completely state controllable. Means we can able to find out we can transfer the state of the system from initial state to the any desired state. So similarly, observability test by the Gilbert. So we need to find out the vector C matrix. If the vector C matrix contains non-zero elements, the vector C matrix contains non-zero elements, then we can say the system is completely observable. Completely observable. So this is how we can find out the state controllability and observability of this given matrix. So here I'll give one problem, simple problem we'll do. So a system is represented by state equation, that is x dot, x1 dot, and as well as x2 dot, means there are two state variables. So which is given as 3, 0, 2, and 4, and then there are variable x1 and state variable x2 plus B matrix 0, 1, and U. Of course, the output matrix is also given with 1, 0 into x. So from this given state of the system, this is state model. This is state equation. This is reference to the state equation, and this represents the output equation. So that's why together we can call it as state model. So he has given the state model for a system. Then we need to find out the controllability and as well as observability by the both Kalman's as well as Gilbert test. So by both Kalman's as well as Gilbert test. So if you look at here, it is a 2. I mean, order of a matrix is 2. N is equal to 2. So if I write the Kalman's test, so for controllability, Kalman test for controllability. So what we do is we write the QC matrix. Kalman test for controllability, you write the QC matrix. So QC matrix, we have the B and AB is enough. Why? Because a to the power of n minus 1. So 2 minus 1. So up to A is enough. So 2 columns will come. So what is the B matrix is 0, 1. This we need to find out the B matrix and as well as AB matrix. AB is 3, 0, 2, 4, and B is 0, 1. So I'll be getting 2 by 2 matrix and 2 by 1 matrix. The resultant will be 2 by 1. So 3 into 0, 0, 0 into 1, 0, then 2 into 0, 0, then 4. So 0 and 4 is going to be the A into B matrix. So just substitute these values in this 0 and 4. So the determinant, if I find out this AD into minus BC is equal to 0. AD into minus B is equal to 0. So here the rank of the matrix is not equal to the order of the matrix. It will be less than 2. It will be less than 2. Order of the matrix is the rank of the matrix will be less than 2 because the determinant of QC will become 0. AD into 0 into 4 minus 0 into 1. So that will be 0. So the rank of the matrix is less than n, that is less than 2. So here it is not equal to the order of the matrix. So the system is not completely controllable. The system is not completely controllable. So by using this observability also we can be tested. Observability also can be tested by using the Kalman test, by using the Kalman's test. Kalman test for observability. So what is the Kalman test for observability? We need to find out the Q0 matrix, that is C transpose, then A transpose, C transpose. So only two elements are there. So you need to find out the C transpose matrix is given. C is given as output equation is given as 1, 0. Output equation is given as 1, 0. C is 1, 0. Then C transpose will become 1, 0 like this. So 2 by 1 will become 1 by 2. Sorry, 1 by 2 will become 2 by 1. 1 by 2 will become 2 by 1. So similarly, A transpose we need to find out. So what is the A matrix we have? A matrix we have is 3, 0, 2, 4. Then this will become A transpose will become 3, 0, 2, 4. Means rows will be written as columns. Columns will be written as rows. So now we'll find out the A transpose into C transpose, A transpose into C transpose, A transpose into C transpose. A transpose into C transpose is equal to 3204 into 1 0. So we'll be getting the resultant of this into this. So 3 into 1 3, 2 into 0 0. So 3, then 0 into 1 4 into 0. So I'll be getting 3 0. So here if you look at it contains the one element as 0. So we cannot say, we can say the system completely not observable, completely not observable. So this is about the Kalman test. You try with the Gilbert test for the controllability and observability. And today we'll end up with this problem. So tomorrow we'll continue.